Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve the following problem. Let fx be the function defined as 1 plus x squared plus so on plus x to the power of n squared. In the polynomial expansion of the derivative f prime x, what is the coefficient of x to the power of r term? A when r is integer that is greater than or equal to 0 and less than or equal to n minus 1, and b when r is an integer that is greater than or equal to n and less than or equal to 2n minus 1. We actually need to treat these two cases separately. But before we get to the coefficients, we first need to obtain the derivative. So let's find the derivative. This is one of the very basic examples of chain rule. So first we apply the power rule to obtain 2 times 1 plus x squared plus so on plus x to the power of n. And according to the chain rule, we differentiate this inner part, which gives 1 plus 2x plus 3x squared plus nx to the power of n minus 1. So now with this obtained derivative, let us address the first case where the degree r can have values from 0 to n minus 1. Aside from this 2 at the front, there are two polynomial factors. To make x to the power of r term, consider choosing x to the power of a term from the first factor and x to the power of b term from the second factor. The product of these two terms must give x to the power of r term. So a and b are constrained by the condition a plus b equals r. Moreover, their values are limited to a from 0 to n and b from 0 to n minus 1. But a and b cannot have every integer value in these respective intervals, because we need to consider the constraints a plus b equals r, and r is from 0 to n minus 1. However, even in the case where r has the greatest possible value of n minus 1, you can easily notice that a can have the smallest possible value of 0, since b can have value of n minus 1. On the other hand, when b equals 0, a can also have the value of n minus 1. Therefore, for a general value of r, the possible pairs of a, b goes all the way from a being 0 to b being 0, which are a, b can be 0, r, 1, r minus 1, and so on, all the way up to r, 0. Therefore, in order to find the coefficient of x to the power of r, we must examine the coefficients for all of these cases and add them up. But we can handle them all at once by introducing a general expression, where we denote b as just b, but denote a as r minus b, where b goes from 0 to r. This is equivalent to choosing x to the power of b term from the second factor and x to the power of r minus b term in the first factor. If we think about the coefficients, the coefficient for x to the power of b term is b plus 1, and the coefficient for x to the power of r minus b term is simply 1. Multiplying these two and this 2 at the front gives 2 times b plus 1 times x to the power of r. Since b can have the value of 0, 1, 2, r, the coefficient for x to the power of r is given by 2 times the summation of b plus 1, where b goes from 0 to r. We can write it as 2 times the summation of just b, then b goes from 1 to r plus 1. And using the formula for the sum of natural numbers, we obtain the result r plus 1 times r plus 2. So that was the first part of the problem, and now the second part of the problem, where r has values greater than or equal to n and less than or equal to 2n minus 1. The process is similar to the previous case, choosing x to the power of a and x to the power of b from each polynomial factor. But the increased difficulty for these higher degree terms is that a and b cannot have values too low, because if one of them has a value too low, it makes the other have a value that is too high so that it cannot come from the two given polynomial factors. For example, let us consider the case where r equals n plus 1. Let us assign the value 0 to a. This makes b equal to n plus 1, but since b cannot have values higher than n minus 1, this pair of a and b is impossible. These are all cases summarized from a equals 0 to b equals 0 when r is fixed to n plus 1. As you can see, a also cannot have the value of 1 because then b must have value of n, which is greater than n minus 1. On the other end right here, you can also notice that b cannot be 0 as well because it makes a equal to n plus 1, but a cannot have value greater than n. So there are limits on both ends, and the only possible range is a having values from 2 to n, while b having values from 1 to n minus 1. Now this is only the case for r equals n plus 1, but we can do similarly for a general value of r that is greater than or equal to n and less than or equal to 2n minus 1, and the result is this table right here. As you can see, we have this possible range in the middle, where the constraints are that a cannot exceed the maximum possible value of n, and b cannot exceed the maximum possible value of n minus 1. Therefore, the possible range for b is that b is greater than or equal to r minus n and less than or equal to n minus 1. And we are almost done. We have this range for b. The coefficient of x to the power of b term is b plus 1. The coefficient of x to the power of a term is 1. And we have constant 2 here. So the coefficient of x to the power of r is given as 2 times the summation of b plus 1. But now b goes from r minus n to n minus 1. There are many ways to evaluate this partial sum, but in my opinion, the quickest way to evaluate this sum is using the formula for the sum of an arithmetic progression when both first and last terms are given. For an arithmetic progression an, when the first term a1 and last term an are given, we can find its sum as a1 plus an times n divided by 2, or in other words, first term plus last term multiplied by total number of terms divided by 2. In our partial sum, b plus 1 is obviously an arithmetic progression, so we have 2 times. The first term is when b is equal to r minus n, so it is r minus n plus 1. And the last term is when b equals n minus 1, so it is just n. And the total number of terms is this minus this plus 1, so n minus 1 minus r minus n plus 1. So we have this divided by 2. And if we simplify this, we simply obtain r plus 1 times 2n minus r, which is a surprisingly short and beautiful result. So now that we have obtained these results, let us take a look at the example where fx is given as 1 plus x squared plus x cubed plus x to the 4th power plus x to the 5th power squared, so n equals 5. Here, the derivative is given like this, and if we expand, we obtain this polynomial expression. Here, notice that for the first case, the coefficients from constant term to x to the 4th power are 1 times 2, 2 times 3, 3 times 4, 4 times 5, and 5 times 6, respectively. And the coefficients from x to the 5th power to x to the 9th power are 6 times 10 minus 5, 7 times 10 minus 6, 8 times 10 minus 7, 9 times 10 minus 8, and 10 times 10 minus 9, respectively. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.